Hi, this is Parisa, and I'm going to explain solutions for the A1 in Reinforcement Learning Basics, Artificial Intelligence course. And the exercise 1 asks us to go into the dream environment, take the predefined cart pole environment, and then move the cart pole 5 steps toward forward and 5 steps toward backward. To learn more about cart pole, we go to the documentation, which shows us the action space has 0 for pushing the cart to the left, which can be considered as backward, and then 1 to the right is considered as forward here. So we define a sequence of actions, 5 forward actions and then 5 backward actions, and we want to keep doing it until it is terminated. To do so, there is a loop defined, and the terminated situation is originally false, and showing that it's not terminated, and as long as it is not terminated, keep doing it until it turns terminated, and then break and come out of the loop. And then it's another loop saying that choose each action from the action sequence one by one, and to take that action you need to call the environment.step function and pass the action to it, which gives you a number of outputs, including the observation from that action and the reward taken by taking the action, and if taking the action results in a terminated or truncated situation, which are Boolean 0 or 1, true or false. And then writing these down, we can see how things are changing in the output. If I want to run this, I'm going to run before and then run this cell to see how it works. So here we can see there are like 1, 2, 3, 4, 5, 1 action and then 5 0 actions, so it's working okay, and then 5 actions 1 and then 5 actions 0, and then it is terminated, so it stops moving. If we want to look into more details, we can see that here it also shows us the observation space, the position and velocity of the car are the first two observed values, and the pole angle and angular velocity. And so shape of 4 gives us the information that this environment is fully observable for these actions, and the reward for each of them is 1 until it gets terminated, and the reward from that point to the rest is 0. So this is 1, and it turns true before it is false, and then after that it's true is always 0 because it's terminated and it's not actually taking any action. So I think that the right thing to do is to stop the process, stop any movement, any taking actions when it is terminated, not after all the 10 stages happened. I know it can be complicated, but I was so obsessed with it that I'm going to replace it with this. So first of all, I want to reset it every time I run it, and then I put an exception here that if it is terminated, we want this exception to come out of the loop and write down terminated for us. And if I run this, when it's terminated, it shows us, and then it comes out. Doesn't matter how many zeros, like if there are 2 zeros, it doesn't do all the 10 steps, it only does until it is terminated. Anyway, so the only thing I wanted also to add is that if you look at the position as we are pushing it toward right, that position is increasing until the action is 0, and also the speed of the vehicle is increasing because we're pushing it to the right more and more. The force is more and the acceleration becomes more, resulting in a higher speed. But when we're pushing it toward left, as explained, it's not going to the left, it's just slowing down according to the high speed it had until it changed the action. So up to here it's just the slowing down, the speed goes negative, and then the location is like still increasing, so it keeps going to the right until this is negative, and it goes a little bit to left, and then again keeps going to the right by taking the right action. It's all about this, I believe, and I hope I explained everything in here. So the next task asks us to reset this environment and see how the initial observation situation is, and what are the boundaries of this environment. Is there any boundary or not? And also do the same for the mountain car environment. So to get the initial card pool observation, we know that by doing the reset, we can reset the environment to its initial situation, but it also returns that initial observation. So we can save it in a variable like this. And so we can have both mount pole and mountain car by doing the environment name dot reset and saving it into these variables. After saving it, we can see the observation like in observed results. As you can see here, there are 4 of them, and then initial position, and you can see the initial position of the mountain observation, and the mountain has, so the observation space has a position of the car along the x-axis and the velocity of it. So it shows that, it shows that a 0 shows that it's not moving in the first place. And then to get the boundaries, maximum and minimum values, I need to write the observation space dot low, which gives us the lowest boundaries, and then high gives us the high boundaries. So I imagine this as like a little mistake. It should be max, and then this should be min, as far as I understand. And if I run this, I didn't run this one. And if I run this, we can see that min. So it gives us the minimum and maximum position for the cart pole, so it doesn't go beyond that bound, and then the minimum and maximum speed, and then the angle and the angular velocity, the same position and speed for the mounted car. Exercise 2 asks us to define an acrobat environment this time and see its boundaries, its initial observation, and what are the actions, how many are they in this information, and take it. And we want to take a random action and take a step in the environment and then get the reward out of it. So the acrobat environment comes from gym.make. This environment is given to the make function to make it initiated, and then the number of actions can be taken by the environment name dot action space dot n. That shows us how many actions are in there, and by resetting it, we can get the initial observation and write it down, which I believe should be like 0. This is better to visually. And then acrobat, and it should be also min, and then for the min again, environment name observation space dot low, and then dot high gives us the max of it. So we can see all of these results here. So there are 3 actions. And initial observation has these values, and the observation limits are given -1 to 1, -1 to 1, and so on and so forth. And before taking the action, I want to take a look into the documentation of it. So this is the mountain car, and this is the cart pole, and this is the acrobat. So acrobat has 3 different actions. 0 is a torque -1, like rotating toward left, and then not moving at all, and then rotating toward right, which results in all these joints and arms movements. In therefore, the observation space includes the cosine and sine of all these angles between the joints, and the angular velocity as well. For the arm, I believe. Yeah, for the arm. Okay, so here you can see, and then we take a random action by doing the environment name dot action space dot sample. So it takes one of those 3 random actions and then writes it down. So this time it's 1, and so we can get all these information: observation, reward, terminated, and truncated, by taking a step toward this random action. And we just want to write the reward. So if so this time it takes 1 action, and then the reward is -1. If I run it again, it might be another action like 2, but still the reward is -1. And that's it. So we want to go for exercise 3. And exercise 3. Oh, one thing I wanted to mention is that, by the way, not hard coding like the previous code, not sample action taking, they are not policies that we use in reinforcement learning. These are only for initialization and know how to use these environments, but the policy is usually trained by the algorithm, which is happening in exercise 3. So the algorithm, the way we see how the things are improving is that to look into the reward at each step and see how it changes along the time. If it's increasing, it means that the algorithm we chose, the policy, is a good one, and it's leading us toward a better reward. But if it's going down, or if it's just fluctuating and staying in place, means that it's not doing the right job, and some maybe adjustments are needed. Okay. So here is like the initial installation of the packages, and then importing them that are required for training. We don't concentrate on how the training is happening. We just want to see how the reward is changing by this training. But so it's a cart pole again, and the action space is taken, and there is a directory log there to made to save the results in, save the history in, and with monitor function, we save it in the cart pole environment monitor. We can give the environment to it in the directory to keep track of the reward and save it somewhere. And the monitor comes from this stable baseline3.common.monitor. And then we want to use multi-layered perceptron for the policy, which is just taken for the PPO as a policy chooser, and the multi-layered perceptron policy is taken, and the environment monitor is given, and verbose just shows how we can look at the results at the end. And also, if you're interested, I don't know if I should explain all of these or not, but the PPO and MLP policy are also should be PPO, so is the stable baseline3, and MLP policy is .PPO. I think there is something not right here. Not sure. Yeah. I got you. Yeah. Sorry, my bad. That's okay. And then, so this class is defined to do the reward callback, which is inheriting from the reward callback class that was the base callback that was imported here. Okay, no, sorry. Yes, I'm doing. I'm just showing the wrong thing. So it's getting the information how to like check the frequency and then log it. So for each step, it it gets a time step from the log there, and then it calculates the average reward during that episode, and then it writes down the number of time steps and average reward for of the last that amount of episodes. So later we can see how it works, like the reward callback as a variable that is defined by this callback class here. So the check frequency is given as 200 and the log there is as given before. It takes the log file from the from this monitored results. So we're going to load and read those data, and also in order to actually monitor it, we need to train it. So for training, we do the environment.learn, and then we define the number of time steps taken, and the callback is the way it shows the result and how it processes the reward values. So reward callback here, if you see, let's run these. I didn't run it. Yes. And while training, it starts showing us some results every now and then. And regarding this function here on step, it's like for all these 20,000 results, time steps, it takes episodes of 200 time steps, as it is in, it should be 200 anyway, it doesn't matter. And over the last, or better to say check frequency episodes, what's going on? It's not running. Okay, it's installing still. And here is where it's processed that it takes the number of calls, it's a remainder to the 200. So if it retrieves the training reward from when it's the time, like when it's it passes every episode. So now I'm just waiting for these to run. I should have run it before. I'm surprised that I didn't. I mean right now, but I did run it before. Okay, I'm going ahead and we can come back and see this later. Anyway, it's going to show the results, like the number of time steps given, that it starts with 200 because we have episodes of 200 by 200 given here by check frequency. and for each 200 it gives what the average reward is for the last 200 episodes, and then it goes to, okay, here it is, 200, and this is the reward for those, and then 400, this is the reward for the last 200, and then 800, and so on and so forth until all the time steps pass. And then what we want to do is to read that reward data from the CSV file that has been saved by the monitor function. That its name is monitor.csv, and then the two top rows seem to be unrelated, and all of the remaining rows, the first column is giving us the reward value in this monitor file. So we read this file and convert it to an array, and we want to plot how the reward is changing. So this is the important part that I think I should have explained, not the rest. And so we define a figure, and it's x, given a size to make it visible better. Right, can make it bigger. And then we want to choose our x equal to the number of reward data that we have, so it's len of reward data, and then we want to plot the range of these x according to the reward data itself, and then we give it the title of reward collected over 200,000 time steps is the title of it, and the x label shows an episode that I think it should be epochs, because and that should be per epoch too, because each of these epochs include 200 episodes, but there are 300 results here. For each episode we have its own averaged reward, and the resulting not running something in between, resulting in the x-axis to be epochs and the y-axis to be that reward per epoch, not per episode. Certain number of episodes. So it asks us if we for the previous training we've been doing like every 200 episodes, but what if we do every 100 episodes? So it's like we call the evaluate policy, we evaluate it by giving it the agents, the environment, and the number of evaluate episodes that is, in this time it's 100, and it gives us two outputs, the mean reward and the standard deviation of it. And if I run this, it shows that like a mean reward over 100 episodes of the trained policy in cartpole environment is this. Oh man, yeah, it's training, it takes some time, and after seeing the results we can also see, this is not part of the task, but we can also see how our policy is working here. So we need to run these lines. Okay, so it's like 500, and that's it. I would like to see these. It's just a few seconds, not long, and you can close it whenever you want. Installing, so whatever is needed is Python OpenGL is being installed for I think showing it on OpenGL environment, showing the animation, and Colab gene render that can render an animation in Colab. Interesting, and image IO as well for loading the images and videos. And then there is a video recorder, and there is a function to render the video and plays us the recorded environment at the end. I might use this code for other usages. It's so good. Okay, can you please? Okay. So here it is. Moving left and then terminated. Okay. That's it. Okay, have a good one.